Welcome to the first part of the Building Real-Time Video AI Applications course. Let's get started. Go ahead and click the Start button below. You should now see a spinning wheel where the Start button used to be. Eventually, that spinning wheel will become a Launch button. Here's what's happening while it's loading. A GPU-accelerated server is being launched for interactive activities. Datasets, frameworks, and software are being installed on that server. When you launch the task, you will see a Jupyter lab containing instructions, activities, and links to guide you through the next sections. While we're waiting, let's go through some basics about what we'll learn. You should know, most of the materials presented will also be included in the Jupyter lab. In this part of the course, we will learn how to build a video AI application. In a modern world, cameras are everywhere, capturing an abundance of data that can be used to generate business insights, unlock process efficiencies, and improve revenue streams. There are limitless use cases, such as reduced vehicle congestion at traffic intersections, health and safety monitoring at hospitals, surveying retail aisles for better customer experience, sports analytics, or at a manufacturing facility to detect component defects, just to name a few. Every one of these applications demand reliable, real-time video AI. At the heart of these applications is one or more machine learning models to generate insights from the video inputs. These are generally deep learning neural network models that have been trained for a specific task. There are numerous approaches for drawing insight from videos using machine learning, such as classification, which is used for identifying the object contained in an image, localization, where the image used regression to return the coordinates of the potential object within the frame, object detection, which includes image localization, can specify the location of multiple objects in an image. Segmentation provides pixel-level accuracy by creating fine-grained segmentation mask around the detected object. Transforming video inputs into usable insights is a computationally intensive task. This type of processing can be done at the edge, near the sensors, on-premise, or in the cloud. Once the AI-based insights have been generated, we can pass them downstream for further processing, such as create alerts based on defined criteria, perform further analytics, or make visualizations to monitor trends and patterns. In order to deploy and manage our fleet of camera sensors, we must develop efficient systems, design the appropriate infrastructure, and understand the implications of our choices. Fortunately, there are some tools that we can use to help with development. Analyzing large amounts of data based on complex machine learning algorithms requires significant computational capabilities. Therefore, this has traditionally taken place in on-premise data centers or cloud-based infrastructure with the most powerful hardware. They can provide massive computational, processing, analytics, volume storage, memory, and graphics processing capabilities. However, a major drawback of this type of development is latency, which occurs when data is collected from sensors and various connected devices and sent back to the cloud. This delay becomes more obvious as the amount of data created and consumed grow, causing bandwidth to be jammed. We want to use stream processing to provide analytics in or near real time. With the arrival of powerful, low-energy consumption IoT devices, computations can now be executed on edge devices. When inference is performed on the edge, we can choose how much of the raw video to transmit along with the AI-based insights. This can provide some benefits. Faster response time, which is particularly meaningful when decisions based on the data processing have to be made immediately. Lower bandwidth cost. Sending raw video captures across a fleet of sensors requires a massive amounts of bandwidth, incurring heavy cost for organizations. Mitigate network-related problems, for example, if there is no or low network connectivity in remote locations. Improve data privacy and security, since edge devices can be programmed to discard sensitive data after it's been processed. AI inference is easier said than done. Since edge devices generally have less computational resources, we need to be able to create a data processing pipeline that optimizes on efficiency without sacrificing accuracy. Let's take a look at one of these applications. Nearly every video AI application uses a similar framework. Generally, A video AI application takes one or more video streams, performs decoding and muxing, or aggregating, pre-processes a batch, and puts the data through AI inference. Afterwards, the AI-based insight combined with the original video can be 1. Encoded with storage, 2. Used to create a composite for display, or 3. Passed downstream for further analytics. There are some challenges when it comes to developing a video AI application. For example, design complexity. Developers need a way to leverage multiple AI models and bring them to production, regardless of the origin of framework. These models need to be optimized and accelerated to run on the target hardware. Total cost to ownership. A good video AI application must consider multiple variables to optimize on the overall cost. That is, AI products differentiate on quantity, speed, and efficiency while being cost competitive. Hardware-accelerated solutions that maximize stream density is a must when creating video AI applications. Deployment flexibility. Video AI applications require the flexibility of being able to run on a wide variety of configurations that range from small edge devices to public clouds. Developers want a platform that will allow them to develop once and deploy in many configurations without having to maintain different software stacks. We're setting out to solve every single one of these problems for developers large and small. The end-to-end development workflow might look something like this. With the TAO toolkit, we start with one of the many production-ready models that have been pre-trained with millions of images to achieve state-of-the-art accuracy out of the box. The model can also be used for transfer learning, fine-tuned, and optimized. This process enables you to create production-quality models with minimal labeled data and training iterations. The resulting models are not only accurate, but also provide high inference throughput. To build a data processing pipeline and deploy the video AI model, we can use the DeepStream SDK, which is a streaming analytics toolkit for video and sensor processing. These tools were created with the end user in mind. They're easy to learn and use as APIs that provide abstraction to the underlying processes. Let's take a closer look at DeepStream SDK. DeepStream is an optimized graph architecture built using the open-source GStreamer multimedia framework. There are 3 key concepts in GStreamers that we need to know before building our application. Understanding the terminology and their role in the application will help us rationalize the syntax for working with GStreamer and DeepStream. Elements are the core building block of the GStreamer. They process the data as it flows downstream from one source to the sink elements, passing through filter elements. Elements provide some sort of functionality when linked with other elements. For example, a source element provides data to a stream, and a filter element processing a stream of data. GStreamer offers a large collection of elements by default, but also allows for writing new elements. DeepStream provides essentially custom elements that are hardware accelerated. Paths are used to negotiate links and data flow between elements in GStreamer. It is the port on an element where links can be made with other elements to allow data to flow through. When data flows from element to element in a pipeline, in reality, it flows from the source pad of one element to the sink pad of another. A bin is a container element which allows you to combine linked elements into a logical group. This is useful when constructing complex pipelines. The bin also manages the elements contained in it, including state changes as well as the bus messages. A pipeline is the top-level bin that also manages the synchronization and bus messages of the contained elements. We've talked at length about plugin model-based pipeline architecture. DeepStream SDK uses plugins that are hardware accelerated. They allow heterogeneous processing on GPU and CPU, hides parallelization and synchronization under the hood, and are inherently multi-threaded and uses efficient memory management. Here's a list of some of the more commonly used plugins that are included in the DeepStream SDK and accelerated using Nvidia hardware. Specifically, we're interested in the NVInfer plugin, which provides TensorRT-based inference for detection and classification. For the most part, all data in GStreamer flows one way through a link between elements. Data flows out of one element through one or more source paths, and elements accept incoming data through one or more sink paths. A sink, in computing terms, is designed to receive data. GStreamer provides several mechanisms for communication and data exchange between the application and the pipeline. Understanding the mechanics will enable us to access data within the pipeline. The bus is the object responsible for delivering to the application messages generated by the elements. Every pipeline contains a bus by default, so the only thing applications should do is set a message handler on a bus, which is similar to a signal handler to an object. When the main loop is running, the bus will periodically be checked for new messages, and the callback will be called when new messages is available. All streams of data in GStreamer are chopped up into chunks that are passed as one of two types, events and buffers. Buffers are the basic unit of data transfer in GStreamer. Normally, a bus contains a chunk of video data that flows from one element to another. The DeepStream plugin attaches metadata, such as those generated by the AI inference plugin, to the buffer. Events, on the other hand, contains information on the state of the stream flowing between two linked paths. Events can be used to indicate the end of a media stream. As the buffer is passing through the pipeline, metadata is progressively attached. We're interested in the metadata generated from the AI inference plugins. At the frame level, we have the number of objects detected, and at the object level, we have the bounding box coordinates and the classification, just to name a few. To access this metadata, we can use probes. Probing is best envisioned as having access to a pad listener. We can use them to access metadata at various points of the pipeline. Technically, a probe is implemented as a callback function that can be attached to a pad. While attached, the probe notifies when there is data passing. This approach allows us to easily interact with data flowing through our pipeline. Since the video AI application will rely heavily on the metadata generated from the deep learning models, the probe callback function might be the most important when constructing a deep stream pipeline. When it comes to optimizing the video AI application, there are several metrics we should consider. Of course, we have accuracy for classification. For detection, we may also want to know the intersection over union or mean average precision. We're also concerned with the throughput of the video AI application, which can be measured as frames per second. It can be used to suggest how many streams our system can handle reliably. Latency is important for real-time pipelines that are time-critical. We can calculate latency measures for the entire pipeline or add individual plugins to further debug and identify rate-limiting processes. Utilization metrics report how busy our GPU is over time and can be used to determine how much an application is using the GPUs in the system. To summarize, the DeepStream SDK contains hardware-accelerated plugins for various stream processing, including plugins for deep learning, multi-stream encode and decode, and image capture and processing. This modular, scalable architecture allows developers to build highly performant real-time video AI applications. To facilitate with the building of your custom application, we also provide a lot of development tools such as reference applications and configurations. We'll cover additional functionality of DeepStream at a later part. For now, let's launch our task.